Hi and hello once again. So we are on the continuation of our discussion on problem solving on lesson number 6, transmission and distribution. So we need to read the problem first. So this is the problem: a short three-phase transmission line with an impedance of 6 plus J8 ohms per wire has a sending end and a receiving end voltage of 120 and 110 kilovolt respectively. Now for a receiving load, which is PR at 0.9 lagging power factor, we need to find the following: the apparent, the active powers, or simply the complex power of the system or transmission line. Okay, now let us have the solution of this problem. Okay, the problem needs first is corresponding per phase analysis. So we already discussed per phase analysis from our last few modules or few problems, and on the fundamentals, of course. So this is the per phase analysis of our problem here, and we have here a three-phase 3-wire, okay, short transmission line. So the given here is magnitudes of your Vs and Vr, your current I, your ZL in terms of R plus JXL, and the receiving power factor. Now the receiving power factor, by the way, is in lagging condition 0.9, and when you have the angle, no, in terms of the inverse of the power factor, we have 25.84 degrees. Now, to solve the problem here, and we need to get the complex powers, okay, of your transmission line on the sending end, rather. So we need to have to compute this one. Okay, in order to do that, we need to recall the important formula that we have discussed on short line. So we have this formula here that your VSN, transmission angle alpha, simply equal to the receiving end voltage, which is our reference, always our reference. It means that all of the angles that you can see on the solutions here are with respect to the receiving end voltage. And then the current, wherein the negative here again, no, is in a lagging condition, and the positive here is on the leading condition. And then multiply by ZL, which is R plus JXL. Now, what we'll do is to substitute all of the values here, and please take note, it must be in per phase basis. So please don't forget to divide the line-to-line voltage, okay, by square root of 3. Please take note, if the problem has a paragraph like this, a 120 volt or 120 kilovolt and 110 kilovolt, wherein it is not specified if that is a per phase or a line voltage, always by default, the values are in terms of line to line, and thus we need to divide it by square root of 3 so that we can use the per phase basis. Okay, now we just substitute all of the parameters here. I forgot to mention the bar zero here, but anyway, it will not affect, no, the equation or the term. Now you have here your current as your lone variable, which is we do not know, the unknown, and then 25.84, the negative here is a lagging condition, and then your ZL R plus JXL. Okay, what I've done is I simplify into numerical values, okay, the value of the 120K all over square root of 3 and 110K over square root of 3, which is 69.284 and 63.51K respectively. Now, to simplify it further, we need to transform this polar entity to its corresponding rectangular, which is this term here, and then 6 plus J8. And what you will do is obviously a little bit of algebra. So you need to simplify this term by multiplying these two here, no, these two terms here. So what will happen further on the problem is simply it will become like this. And then you have 8.8869 plus J 4.5849, multiply it by the current, which is our unknown. Now, since you can see on this term here, we have two unknowns. And you will think that there's no solution. But there is a solution here by separating the real and imaginary parts. So a little bit of advanced mathematics here. At least we separate the real and the imaginary terms. So the real here is definitely without any j's or without any I or j. If it depends on how you will name the j parameter, but I usually use the j parameter here, which is the imaginary entity, so which is square root of -1. So what will happen is I separate already the real and the imaginary terms here. So a little bit of what we have discussed on AC circuit analysis, by using the Euler identity on complex number, and we arrive in terms of magnitude only, this term that z squared is equal to the real and imaginary parts squared, okay, which is the total phasor z, which is, it will come from this entity, right? X plus jy, real and imaginary simply equal to the phasor z bar angle theta. So what we do is we separate real and imaginary parts, and then this overall phasor entity, which is 69.284K, you need to square this without the bar angle. And then you have this 63.51K plus 8.8869. But anyway, what I've done here is I already eliminate the bar 0, simply because it will not affect the term. Okay, so we just squared that here, as well as the 4.5849i. We also squared it. Now you can now see that we have only one variable that is left, which is your I. So we need to expand this further. Since our board is not, our solution will not fit on the board anymore. So I leave the simplification in terms of your algebra, that x plus y squared, which is this, simply equal to x squared plus 2xy plus y squared. Then on our next slide, we will conclude the solution of this problem. Please stay tuned. Okay, so let us conclude problem number 3, okay, of our problem solving on transmission and distribution. So from the last slide, we pause on the simplification of x plus y squared, and then when we apply it to the equation from the last term or last equation, we could have this result. Okay, so you have 48 times 10 to the 8, 40.335 times 10 to the 8, and then the 1.128 times 10 to 6i, and then the I squared terms of 78.97 and 21.02 respectively. Now we can simplify this further so that we can have a quadratic equation in the form of 100i squared plus 1.128 times 10 to the 6i minus 7.667 times 10 to the 8 equal to 0. Please take note, this is my own solution in terms of 4 decimal places, but what will happen is just for accuracy purpose, but it's your choice if you want to have 2 decimal places or 3, but I usually use 4. Okay, now I use the formula of the quadratic equation, so we can recall this one from your basic mathematics. Okay, that you can have the roots of I1 and I2 by substituting the A, B, and C here on the quadratic equation. And if you do so, we can yield with 2 results. Now the result is a 641.04 ampere for the first root, which is in terms of the current, and the second root in terms of negative 11,920 amperes. Both of these values are the same, Okay, you can substitute that, it will yield with the same answer. However, it is much practical if we use the lowest current. Please take note the negative value here. It means inverse or an antiphase. The assumption of the current is wrong. So you need to multiply it by -1. But that is only current. But in terms of the current, I suggest or strongly suggest we must use the lowest value. Simply because a lower drop, it will yield with a good result in terms of the efficiency. I usually use on my calculations in terms of experience, if I have this kind of problem, I use the lowest. Although it is negative here and positive here, I usually use the lowest and then I just get the absolute value. But in this case, we're lucky it is positive. So 643.04. So it's good. But if this is both negative, I will usually select the lowest magnitude value. Okay, therefore we just substitute on the basic, okay, three-phase balance equations in terms of complex power, in terms of the receiving. We need to get the receiving values here in terms of the load. So your PR square root 3 VR IR power factor at the receiving end. So we just substitute the 643.04 there multiplied by 110k square root 3 times 0.9. It will yield with 110. It is megawatt, not watt. That is too small. Sorry for the mistake here. Okay, just a little bit of error in terms of the how I write. 110.26 megawatts. Now, in terms of QR, you have your square root of 3, 110k, 643.04. This 0.4358 is based on the sine angle theta, which is the sine of 25.84. Okay, and this one is terms of the cosine of 25.84, which is 0.9. So it will yield, okay, with the value of 53.39 mVAR. And using the basics, in terms of the magnitude, in terms of the complex power S, or the apparent power, PR squared, QR squared square root. The answer is 122.513 MVA. So from that, we can now move forward to another set of problems. Problem number 4.